Yeah. Hello, everyone. This is NPTEL course Functional Analysis. Okay, I hope the recording is on. Yeah. This is the NPTEL course Functional Analysis, and this is the problem solving session. Here I'll explain some sample problems from the assignment, which will help you solve the other problems. Okay, and which will help you to understand the concept better. We are in week 11. This is MRFTA on Kumar Raikwad. Okay, so let's get started. Question number one. Okay. Question number one says, let H be a Hilbert space over C. Let P be an orthogonal projection onto a proper non-zero subspace of H. Which of the following statements are true? First of all, the orthogonal projection means we know that P star equals to P and P square equals to P because it's orthogonal and a projection. Yeah. Okay. So options are the eigenvalues of P are real, minus 1, 0, 1 of the eigenvalues of P, and the only eigenvalues of P are 0 and 1. Okay, let's see. So we have P as a projection. So suppose let lambda be an eigenvalue, which implies that there exists in X such that Px equals to lambda x, right? But then if you again apply P, you get P square x equals to lambda Px, which is again lambda x, which is lambda square x. But what do you know is P square equals to P. That implies P square x is same as Px, which is same as lambda x. From 1 and 2, we know lambda square x is same as lambda x. That implies lambda square minus lambda 0 because x is non-zero, we know. That implies lambda equals to 1 or 0. Yeah. So these are the only possible eigenvalues. So these are real numbers, of course. So eigenvalues of P are real. Minus 1, 0, 1 are eigenvalues? No, because minus 1 is not the possibility. The only eigenvalues of P are 0 and 1. That's correct. Check the recording once. Yeah, working well. Okay, so I hope this is clear. This was very easy question. Okay, we'll go to the next question. Consider the real Hilbert space L201, space of all integrable function, not just integral, square integrable. Let A belongs to LH be defined by AF at T equals to TF of T. Which of the following statements are true? Okay. The first is to check whether A is self-adjoint. Yeah. So let's say what is inner product of AF with G? I mean, where F comma G belongs to, like, I'll call this as H for the moment. So which is integral from 0 to 1 AF at T into GT bar dt, which is integral 0 to 1 TFT GT bar dt. Yeah. But what I can write is I'll just take T inside of this conjugate. This will remain as it is because T belongs to 0 to 1. This is a real number. So there is no point in taking the conjugate of T. So this is just same as integral f with ag. Yeah, because ag will be t times gt. ag at t is t gt for every t. So from here we observe that a star is same as a. That means a is self-adjoint. Yeah, no problem in that. Now we have to check whether a has infinitely many eigenvalues or like what are the scope of eigenvalues here. First of all, A is a linear operator on Hilbert space L2. Okay, this is what we know. Now suppose let lambda belongs to R. We are in real we are in real Hilbert space. Okay, be an eigenvalue, or instead of saying eigenvalue, be such that Ax equals to lambda x for, or because we are in function space, I write it as f. Some f belongs to h. Yeah. So if we can find a non-zero f, then with some conditions on lambda, then that lambda will be an eigenvalue. But if we show that f is 0, that no matter what choice of lambda you take, then that means A does not have any eigenvalues, right? Because if lambda is an eigenvalue, then there exists a non-zero f such that this holds. So let's see how it goes. So AF at t should be equals to lambda times f at t, right? That means t times f at t should be equals to lambda times f at t for all t belongs to 0, 1. That means t minus lambda times f at t should be 0 for all t belongs to 0, 1. That means except for all t not equals to lambda, f at t has to be 0. Yeah. But now, I mean, you can, at first glance, you can say that f need not be 0 because it's just square integral function. So even if you put f at lambda non-zero some non-zero value and everywhere else 0, then it's not a 0 function. I mean, in a function sense. But we know the L2 space is not just space of functions; it is space of all equivalence classes. Yeah. So because f is 0 on all t, I mean, since f at t is 0 for all t belongs to 0, 1, t not equals to lambda, that implies f is identical to 0 almost everywhere on 0. Yeah, almost everywhere means except for a set of major 0, and singleton lambda is of course a set of major 0. Hence, f is identical to 0 almost everywhere on 0, 1. That means f is a 0 element of L2 0, 1. Yeah, that means we have proved that if AF equals to lambda f, then f has to be 0. That means lambda is not an eigenvalue. And we haven't started with any conditional lambda. So no lambda qualifies to be an eigenvalue of this operator A. So A does not have an eigenvalue. It has no eigenvalues. So option B is very far away from being true. It says it has infinitely many eigenvalues, whereas there are no eigenvalues. So, okay. So done with question number 2. Okay. Let's go with the question number 3. Consider the real Banach space V, which is C01, and the operator A. Okay, it's the same operator, AF at t equals to TFT. Which of the following statements are true? But the space is C01 here. Okay. Okay, and when we are saying it as a Banach space, that means we are having the infinity now. Okay. So now whether we have to check whether A is compact. So an equivalent definition of compactness is every bounded sequence, I mean image of every bounded sequence has a convergent subsequence. And this was a condition. This has to be satisfied by a compact operator. Yeah. Let's see if this operator satisfies. If we take the sequence fn given by fn of t equals to t power n. Yeah, so this fn belongs to C01, which is V essentially in this example. Fn is bounded, and what is AFN is AFN at t equals to t times Fn at t, which is t raised to n plus 1. That means simply AFN is just Fn plus 1. There's nothing different. The same sequence in particular, just starts from the second term. Yeah. So does AFN have a convergent subsequence? So what do you mean by a convergent subsequence? We are in the space C01. Yeah. So in C01, if any sequence converges, then that sequence has to converge pointwise as well. In C01, if Fn, okay, Fn is already there, suppose Hn converges to H, then this should imply that Hn at T will converge to H at T, for all T belongs to 0, 1, yeah, pointwise convergence. But what we can see here is, for the whole sequence AFN, what is AFN at T? It is T raised to n plus 1. This converges to 0 if you take any element in between 0 to 1, strictly less than 1, but it goes to 1 if t equals to 1. Yeah. So this will happen with any subsequence. If you take any subsequence of AFN, this will converge to the same function. Yeah, pointwise, if you see. So if there exists a subsequence of AFN which converges in norm to another L function f, then that function is again the same function. Yeah, because pointwise it has to converge to 0 or 1. But now the AFN, like even if you say AFNK, a subsequence is a sequence of continuous functions. Hence, it cannot converge discontinuous to a discontinuous function. Yeah, this is a discontinuous function. So that's done. AFN, which is essentially the Fn after starting from the second element, cannot have a norm convergent subsequence. That means is need not be compact. So the first one is wrong. Okay, let's go with the other one. Yeah, we have just shown that A has no eigenvalues, so this is okay. Okay, so let's go with the spectrum. Spectrum of A is given by root 0, 1. Okay, let's see. Spectrum of A is, if we do the definition, is set of a lambda belongs to, okay, we are in real space. Yeah, such that lambda I minus A is not invertible. Yeah, so let's see. What is lambda I minus A f at t, which is lambda f at t minus T f at t, which is lambda minus t ft. So if lambda belongs to 0, 1, that means lambda I minus a f at lambda will be 0 for all f belongs to 0, 1, which means range of lambda I minus a is a proper subspace. Yeah, all those functions who doesn't vanish at lambda are not there in the range space. That means it's not invertible actually, because it's not surjective. It's not invertible, that means if lambda I minus A is not invertible, then lambda belongs to spectrum of A. So what we got is closed 0, 1 is contained in spectrum of A. Cool. Let's see the other direction. So if suppose lambda doesn't belongs to spectrum 0, 1, yeah, then what do you have? Lambda I minus A f at t is equals to again same lambda minus t into ft. So but this time claim is that this is an bijective function, bijective operator, yeah, because 1 1 it follows, yeah, because if lambda minus a f t is 0 for some f, then ft has to be 0 for all t, because of continuity it follows for all t, f is identically 0. So lambda I minus a is injective, it's straightforward. Now if okay, now let any g belongs to v, yeah, define f as ft equals to gt upon lambda minus t. This is well defined because lambda doesn't belongs to 0, 1. Yeah, so this is nicely defined. Okay, this implies lambda I minus a of f is g. That means lambda I minus a is surjective. Since lambda I minus a is surjective and injective, and the operator lambda I minus a is continuous from v to v, that means by bounded inverse theorem its inverse is also continuous. Yeah, by bounded inverse theorem is also continuous. That means, yeah, that means we are done. That means lambda I minus a is invertible. That means lambda doesn't belong to spectrum of it. So lambda, if not in 0, 1, it does not in the spectrum. That proves that spectrum of A is just 0 to 1. Yeah. Okay. Yeah. So this option is right. I hope it's clear. Save the recording ones. Just 1 minute. Okay. Let's go to the next question. Question number 4. P from 1 to infinity, strictly less than infinity. Consider the complex space LP. And now consider the operator on LP, continuous operator, continuous linear operator, which is the left shift operator. Which of the following statements are true? Its norm is 1, its spectrum is the closed unit disk, and condition. Okay, let's see. Option 1. What is norm AX? Okay, it is just summation. Okay, just to P if I do summation modulus of xi power P I going from 2 to infinity. Yeah, but if this is less equal, just add the first term P, which is, yeah, that means norm AX is less equal norm X. This is happening for all x belongs to LP. That means norm A is less equal 1. But for x equals to E2, norm x is 1. And what is norm AX? This is norm of E1, which is again 1. That means norm A is 1. Now what is the spectrum? Okay. First of all, okay, how to go for the spectrum? Can we go through eigenvalues? If Ax equals to 0, what do we have? My implies x2, x3 and all those equals to 0, 0, 0. That means only null space, null space of T is just span of E1. Does that work? Hmm. Okay, let's see. If we define x, okay, if let lambda belongs to R such that R or C complex Banach space, such that modulus of lambda strictly less than 1, define x as 1 lambda, lambda square, lambda cube and so on, then is summation modulus of lambda raised to I whole raised to p, yeah, I'm going from 1 to infinity. This is finite because mod lambda I is strictly less than 1. So this is finite, we know. What is Ax? Ax equals to lambda, lambda square, lambda cube and so on, which is lambda times 1 lambda, lambda square and so on, which is just lambda times x again. Yeah. That means, okay, and x is known, that means lambda belongs to but lambda is an eigenvalue and essentially it belongs to spectrum. Okay, that means set of all lambda belongs to C such that mod lambda strictly less than 1 is contained in spectrum of it. And spectrum is closed set, that means its closure is also in the spectrum. Closure, which is equal 1, is contained in spectrum of it. Okay, we got one side. Now the other side. Claim spectrum of A is contained in this set. Okay. Hmm. Okay, let's say what is lambda I minus A of x. This is lambda x1, lambda x1 minus x2 and lambda x2 minus x3 and so on. Okay, so if lambda doesn't belongs to, I'll call this D, a closed unit disk D, then we know that lambda I minus A is 1 1. Yeah, this we know because the eigen values are contained in the spectrum of this set. We have shown it. Oh no, we haven't shown it. Okay, let's see. Or do we? Yeah, so if let's see, if lambda I minus x is 0 for some x, and that means lambda x1 minus x2 is 0. That means x2 equals to lambda x1. Similarly, x3 equals to, from this, x3 equals to lambda square x1 and so on. That means x has to be equals to x1 then lambda x1 and so on, which is sometimes this vector itself. Okay. And yeah, and if mod lambda is strictly greater than 1, then x doesn't belong to LP because we know that this summation goes to infinity if mod lambda is strictly positive. Yeah, that means this is not this will be injective. Yeah, so the only condition that this x belongs to L2 is x equals to 0. X has to be 0. That means lambda I minus A is injective. Now let's see if it's bijective, because if it becomes bijective, then we are done. Okay. So if lambda x1 minus x2 comma lambda x2 minus x3, this sequence I have to equate to some other elements for y1, y2 and so on, belongs to L2 again. Then what I get is okay, I'll write x2 equals to lambda x1 minus y1, then x3 equals to lambda x2 minus y2, which is lambda squared x1 minus lambda y1 minus y2. No, this is not going anywhere. Good. Okay, what else we can do? Hmm. We don't have to do anything like this. Okay, okay. Because what we know is spectrum of A, I mean, is contained in any lambda belongs to C such that modulus of lambda is less equal norm A. Yeah, oh, okay, I forgot that. This is totally unnecessary. Yeah, this we know, but this is because norm A is 1. Oh, so this is contained in that. So one side we already proved that this side is contained in spectrum of A, and now this is ready made to have. Spectrum is contained in this. So what we know is spectrum of A is equal to, so for lambda belongs to C, so that mod lambda less equal 1. Oh, but one should try that subject to case also. That's interesting. So this is we know, and this is wrong because it's true for all B. Yeah. Done with question number 4. Let's go with question number 5. Okay. So again, P from 1 to infinity not equal to infinity. Consider the complex Banach space LP. P is operator defined by AX is this. Okay, so we want to check what is the spectrum of A. Okay, first thing we can notice from directly from the definition is AEI equals to BIEI. Yeah, for all standard vectors CI. Yeah, just a minute. Yeah, that means BI are all eigenvalues. Yeah, that means the whole B is contained in the spectrum, and because spectrum is closed, that means B closure is contained in spectrum. So the first one is all ready made. Okay, so we have to check whether this is the whole spectrum. Okay, okay. So our first of all, okay. Let's see. If suppose you take lambda which is doesn't belongs to B closure, okay. Let lambda which doesn't belongs to B closure. That means if you call beta to be infimum of maybe modulus of beta I minus lambda, because it's strictly positive, we know, because it's not there in the closure. Yeah, so its distance from the whole B has to be positive. This is positive. Now, what can we say about the lambda I minus? Is it 1 1? Is it on 2? Because if it's 1 1 and on 2, then we are done. Then it will be invertible, hence lambda cannot be in the spectrum. Yeah, because we are already on the Banach space, continuous, and operator A is continuous. So let's see. Lambda I minus A at x, suppose is 0. That means lambda x at I minus beta I x at I is 0 for all I. That means lambda minus beta I equals to 0 for all I. Yeah. But then what this imply? If x is non-zero, yeah, if x is non-zero, then lambda has to be equal to beta I for some I at least. For some I. But this is a contradiction because we have chosen lambda which is not in whole the B complement. Yeah. That means lambda I minus A is injective. One thing is done. If we know lambda I minus A is injective now. So is it surjective? That's the question. Is lambda I minus A surjective? Let's see. Let any element of Y belongs to space V again. V is we call it, yeah. I mean LP, okay, just take LP. LP. So if let's see what's the pre-image of this Y. That means we get lambda x at I minus beta I x at I equals to Y at I. That means x at I so equals to yi upon lambda minus beta I. Yeah. Does the question is does x belongs to LP? It is summation modulus of xi power p I going from 1 to n, summation modulus of yi upon modulus of lambda minus beta I going from 1 to n. But we know lambda belongs to B closure, doesn't belong to B closure. That means this term is positive. This is strictly less than. I can take 1 by beta or p outside, and then it is just summation yi power p I going from 1 to n, which is less equal norm y. That means, yeah, that means we are done. That means this series converges. That means x belongs to LP, which implies lambda I minus A is surjective. So we have a bijective operator from a Banach space into a Banach space, bijective continuous operator. Hence, by bounded inverse theorem, lambda I minus A is invertible. Oh, so if lambda minus is invertible for all lambda doesn't belongs to B bar, that means spectrum is contained in B bar. So we are done. Spectrum of A is 0? No. It's all B bar. Okay, so fifth one is done. Oh, wait. It's working. Okay, let's go to question number 6. I hope it's clear. Question number 5. Question number 6. Let A belongs to set of all linear operators on L2. Which of the following cases A is compact? Okay. So all these operators are same as before, like Ax at I defined as beta I x at I. Yeah, where in first option this beta I is the sequence I minus 1 by I. In second option this beta I is just this sequence. I mean 1, 2, 3 up to 7 and then all 0. And the third one, this is the sequence sorry, 1 by 2 power I minus 1. Yeah. Now this is the standard result. This kind of operator, this A is compact if and only if the sequence beta I converges to 0. Yeah, this is what, because all beta i's will be eigenvalues here, because AEI's will be BIEI's, same as before. But what we know is the only limit of the only limit of eigenvalues of a compact operator can be 0. 0 is the only possible limit point. So it's compact when only if this happens, because here all the BI's are convergent. Yeah. So the first one you can directly say no, because this guy I am minus 1 by I converges to 1 as I going to infinity. And this is true because it's just a finite rank operator, right? It's just a span of E1 through E7. Just a minute. Just 1 minute. Yeah. Okay. So yeah, the second option is a finite rank operator, so hence it's compact, no problem. And third one, the sequence I 1 upon 2I minus 1 is converged to 0 as I going to infinity. This one is also good. So let's stop. No, it's working. Okay. So all among these three, the second and third one are compact operators. First one is not. Yeah. Okay, that's clear. Just a minute. Yeah. Let's go to the next question. Let V and W be Banach spaces and T from V to W be compact. In which of the following cases will T be the limit of operators of finite rank? Okay. This is explained in the class. I mean, the whole if the first option V and W are Hilbert spaces, hence any compact operator is now a limit of a finite rank operator. So this is true, and these two are also true. That are explained in the class. Yeah. We can refer lectures. It is completely explained the whole three cases in the class. Okay, I'll leave this to you. Maybe we'll go to question number 8. Okay, just a minute. There's some problem with this iPad. I don't know why I'm not able to write. Just 1 minute. Okay, yeah, it's working. Yeah, okay, yeah, it's good, it's working. Yeah. Okay, so question number 8. TF is defined in this way. Oh, this is the, yeah, see, in this kind of operators, this is referred as the kernel. Yeah. And we have a result whenever this kernel is bounded, then the operator is this Hilbert-Smith operator. Yeah. Here, sine of x plus y, which belongs to, is bounded. That means t is a Hilbert-Smith operator. But every Hilbert-Smith operator on this inner product space is compact. It's continuous. It's natural. Then T is compact also, and every compact operator on Hilbert space is the limit of operators of finite rank. All these three follows. It's just the Hilbert-Smith operator theory. Okay, it's nice, quite nicely explained in the class. Maybe you can refer the same class videos. Then we'll go to question number 9, which says that T is operator from L2 to L1. Which of the following statements are true? Okay, T is compact. So this is a big statement. It's saying every continuous linear operator from the space L2 to L1 is compact. Yeah, let's see if this follows. The big statement. Let T belongs to L2 to L1. Now, is it compact? Compact equivalent definition of compactness is image of every bounded sequence has a convergent subsequence. Yeah, this is an equivalent definition. The other definition is image of every bounded set is relatively compact. Yeah, but in a nonlinear space, a compact set is equivalent to saying it's sequentially compact. So that's the same, because the image of every bounded set is bounded, then every bounded sequence there has a convergent subsequence, means it's sequentially compact, means it's relatively compact, means it's compact. Okay, let's see if this follows. Okay, so let maybe xn, now this xn is the sequence of sequences contained in L2, be a bounded sequence. Okay, so there will be a series of arguments here. Now this xn is in L2. L2 is Hilbert space, which implies reflexive. And we know that in every reflexive space, by the great theorem of Eberle-Schmillian, every bounded sequence has a weakly convergent subsequence. Okay, I don't remember the spelling. That is Eberle-Schmillian theorem. Xn has a weakly convergent subsequence. Yeah, say x and k. Now x and k is weakly convergent. That means a, because a is a continuous linear operator. Okay, t we have. That means t of x and k is also weakly convergent in L1. Yeah, but L1 by Schur's lemma, by Schur's theorem, actually it's a theorem, weak every weakly convergent sequence in L1 is convergent in norm. Yeah, that means what we've got is T, X and K converges in norm. So as a brief summary of the whole arguments, we started with the bounded sequence in L2, and then we got a weakly sorry, then we got a convergent non-convergent subsequence Tx and K. That means every bounded sequence the image of every bounded sequence has a convergent subsequence. So that's it. That means T is compact. Yeah, I hope it's clear. Okay. Yeah. The second one, if T is onto, there exists a right inverse for T. Yeah. Okay. So yeah, this follows straight away. I mean, there is okay because a kernel T is closed, so it's complemented, and this is a standard argument used in so many lectures that this implies that T has right inverse because it's onto right inverse. So if T has right inverse, but okay, I mean at least this follows till now that if T is onto and of course then T has right inverse. But what will follow further is this is true that if we consider T composition with the right inverse of T, I mean instead of calling it inverse, I'll call it R, suppose say R. Then this will be a mapping from L1 to L1, correct? But this is compact because a T is compact and this is a continuous inverse. That means this is a compact operator, compact identity operator on L1 to L1. That means L1 has to be finite dimensional, but this is absurd. It's a contradiction because L1 is infinite dimensional. So T can never be on. So actually the statement B doesn't make any sense. I mean, you can always say B implies Q is always true if P is never true. So that's a propositional trick. Okay. Hmm. Okay, so the ninth one is done. So let's go with the last one, question number 10. Okay. So if T is an operator from C0 to L2 continuous, which of the following statements are true? Okay. So first of all, the note we will use here is, or I will call it lemma maybe, that T compact, sorry, T star compact implies T compact. I have to check whether it's if and only. Yeah, of course it's if and only, because T star star is against star T. So, but now if suppose T is in C0 to L2, that means T star will be from L2 star to C0 star. But the good luck is L2 star is again L2 and C0 star is L1. It means T star belongs to L of, in a way, I can say it belongs to L2 to L1. And what we have just seen in question number 9 is any continuous operator from L2 to L1 is compact. That means this T star is compact, which implies T is compact. Okay, this was rather easy. T is compact. Now, if T is injective, then its range is closed. The third option says if the range of T is closed, then it cannot be injected. Okay, let's see. If range of T is closed and suppose T is injective, yeah, it means what? T from C0 to range of T is bijective operator from Banach space to Banach space. Not just bijective, it's compact as well. That implies by bounded inverse theorem, that means by bounded inverse theorem, what we have is this T inverse is continuous. Yeah, when the inverse is taken from range space of T to C0. But this implies if you combine it with T composite T, and this will be from C0 to again C0 identity mapping. That means, and because T is compact, T inverse is continuous, implies this the whole mapping is compact. Yeah, but this is not possible because C0 is finite, C0 is infinite dimensional. This is not possible. That implies T cannot be injective. Like if range of T is closed, then T cannot be injective. So option C is, yeah, it's correct. Yeah, so this is wrong. I mean, the injectiveness and range being closed are mutually exhaustive in event. I mean, if one happens, then other cannot happen in this condition. So we have just proved this mutual exhaustiveness. Hence, option third is correct, which says range space of T closed, then T cannot be injective. But option B is wrong because it says if T is injective, then range is closed. But both cannot happen. Yeah. So I hope everything is clear. Let's see. Yeah. So yeah, question number 9, 10, and 8. 1. Okay. Okay. So thank you so much for attending session. So the week 11. Okay, so see you all on the next session.